Welcome to the session. Today we are going to discuss trees and their properties. So a graph, what is meant by a tree? A graph G is called a tree if it is connected and has no cycles. So a connected without having any cycle is known as a tree. It immediately follows that a tree has to be a simple graph because loops and parallel edges from cycle. The graphs shown below, which are all are trees. Let us, we are going to concentrate on this. If I am going to consider, this is a graph and this does not have any cycles, so it is a tree. It is a tree. Or if I am going to consider any graph which is of this form, so this is also a tree. Or else if you are going to consider another graph, let us say the graph is this. So this graph is also not having any cycles. So all these three graphs are known as a trees. Let us go for the other graph. We are going to consider a graph which is of this form. And now, this is one graph. Another graph I am going to take like this. And another one is, let us have to consider a graph which is having like this. These are the vertices. And now, this is. So here it is G1, let us consider G1 and this is G2 taken together. So now in this G1, it is a connected, but it is having a cycle. So it is not a tree. It is not a tree. And this graph is, or it does not have any cycle, but it is a disconnected graph. So this is also not a tree. This is also not a tree. And moreover, any pendant vertex, which is known as the leaf of the tree. Suppose if pendant vertex means any vertex degree is 1, then that is known as a pendant vertex. So here the first one is G1 is not a graph and G2 is also not a graph and it is a disconnected graph, and in this G2 different components will be there. Component is nothing but a connected subgraph. So this is one connected subgraph and this is another connected subgraph and this is another connected subgraph. So here there are 3 connected subgraphs. So this is one connected subgraph and this is another connected subgraph and this is another connected subgraph. So which is having, each connected subgraph is having one component. So it is having 3 components. Moreover, so the graph is disconnected. When we are going to consider G2 is a disconnected one, but every component is a connected one. So it is not a tree, but we are calling it as a forest. It is known as a forest. That means the forest is nothing but a connected, which is having components. So then that graph is known as a forest. Now let us go for the properties. And here the theorem, in a graph, there is one and only one path between every pair of vertices. So this we have to prove. Let us go for T be a tree. It is given in a tree, there is one and only one path between any pair or every pair of vertices. So whenever if it is a tree, then it is known as a connected simple graph. If it is a connected simple graph, there is at least one path between any 2 vertices. If it is a connected, then definitely there is a one path between. Suppose if I am going to consider this, and here it is a connected graph. So between these 2 vertices there is a path. And this is one connected graph. Let us say I am considering from these 3, we are having one path. one path. So like that, any connected graph will be there. Definitely between two vertices, definitely there is one path, at least one path is exist. If there are two paths will be there, suppose if I am going to take, if there are two paths will be there, then between the pair of vertices, then the union of these two paths will form a cycle, So here, let us go for this. So from this vertex and next here what this vertex, and this vertex. Let us say, I am just saying that between these two vertices, let us say V1 and V2. Between V1 and V2, there is one path like this. Like this I am going to get. And next another one is, if I am going to consider from this, another path is also going to be exist. V1, V2, V3. Let us say that. So one path is V1, V2, V3, and another path is V3, then V1, and next V2, V3, V1, V2. So if I am going to combining this, then it is a possibility of getting a cycle. So then if it is a cycle, then automatically it is not a tree. So that there should be more, at least one path will be there between two vertices, and if there are more paths are exist, then it forms a cycle. So it does not belong to it will never be a tree. So for that, there is only one path between any pair of vertices that we are going to consider. So here, in this way, that means whenever if I am going to take the tree, then definitely it has only one path between every pair of vertices. If I am going to consume more than one path, then naturally the union of those two paths will create a cycle. Then the graph will not become a tree. So for that, there is only one path between every pair of vertices. And the second one, in a graph G, there is one and only one path between every pair of vertices, then it is a tree. So here it is opposite. So whenever tree is given in the theorem 1, and we are going to prove this, and next conversely, that means there is one path will be given. Now we have to prove that it is a tree. That means conversely. So here it is nothing but there is one path between every pair of vertices. Then automatically G is a connected graph. Since there is only one path between every pair of vertices, so G cannot have any cycle. Because if it is having any cycle, then there is more than one path is exist. So graph which is not having any cycle, moreover it is connected. So we can say that it is a tree. Then if I am going to combine these two theorems, theorem 1 and theorem 2, then we can say that the graph is G is a tree if and only if there is only one path between every pair of vertices in G. So that means theorem 1 and theorem 2 we are going to combine, and we are going to denote that as a graph is a tree if and only if. That means if condition is this and else condition is this, then we are going to prove in this way, in this manner. Now let us go for the another one is a tree with n vertices, and it is having n minus 1 edges. That means a tree which is having 3 vertices, then it has only 2 edges. A tree which is having 7 vertices, then it is having 7 minus 1. So it is a 6 edges. So the total number of vertices minus 1 number of edges. This we have to prove. So we have to prove this by using mathematical induction. So induction method. So here it is obvious for n is equal to 1, n is equals to 1, vertex is 1, then number of edges are 0, there is no edge. So to connect that vertex, so number of vertices are n minus 1, that is nothing but n is equals to 1 minus 1, it is equals to 0. And suppose if I am going to consider two vertices, then I can connect like this. So if I am going to connect like this, then it is not a tree. Then it is not a tree. I have to connect like this only. So then only it will become a tree. So number of edges will become m is equals to 1. Number of edges will become m is equals to 1. So number of vertices are 2. So 2 minus 1, that is number of edges are nothing but 1. So now if I am going to consider another a graph which is having a tree which is having 3 vertices, then automatically it is having 2 edges. It is having 2 edges. So I cannot construct another edge like this. If I construct like that, then it is not a tree. It is not a tree. So the result is obvious for n is equals to 1, n is equal to 2, n is equal to 3. Now by induction we can say that we are assuming that this is true for a tree which is having k number of vertices. K number of vertices. So for that it is true. Now we are going to prove that it is also true for a tree which is having k plus 1 vertices. K plus 1 vertices. Okay. Let us, since a tree is a tree, there exists no other edge or path from u and v. Therefore, so for this I am going to, this is the assumption step, and we are going to consider a graph. Let us say a tree which is having k plus 1 vertices. K plus 1 vertices. Now we are going to prove that the theorem is true for this. Then obviously we can say that the theorem is true for any number of vertices. Any number of vertices. So suppose if I am going to consider a tree which is having k plus 1, which is having k plus 1 vertices. Let us say I am just taking k plus 1 vertices. Then let us assume that this is the tree which is having k plus 1 vertices. Now here I am just connecting, let us say u and v are any two vertices in this, and there is only one path connecting this. So I am going to take it as E, edge is E. I am going to consider a tree which is having k plus 1 vertices. In that I am going to consider one edge E which is connecting the vertices u and v. So now if I remove this vertex, if I remove this edge, the graph is disconnected. The graph is disconnected. That means that the tree is disconnected and it will become a component. So each component will be a connected subgraph and which does not having any cycles. So it is one subtree and this is another subtree. This is one subtree and this is another subtree. And T1 is having lesser number of some vertices it is having. Let us say k1 number of vertices. And T2 is having k2 number of vertices. T1 will have k1 number of vertices and T2 will have k1 number of vertices. And we are assuming that the theorem is true for k number of vertices are lesser than that. Then, because then we can say that T1 is having k1 minus 1 edges, T2 is having k2 minus 1 edges. K2 minus 1 edges. Because whenever if you are going to remove one edge, then the graph is disconnected and it is having two components, T1 and T2. Each one is nothing but a tree which does not having cycles. So T1 is having how many edges? K1 minus 1 because it is having k1 vertices, and T2 is having k2 vertices. So it is nothing but k2 minus 1 edges. Then the total number of edges in T1 and T2 is equals to k1 minus 1 plus k2 minus 1. K2 minus 1. Subsequently, we are going to get k1 plus k2 and next minus 2. K1 plus k2 minus 2. So here, it is nothing but K1 plus K2 is nothing but the total number of vertices. The total number of vertices in that is nothing but K. What is this? This is nothing but the total number of vertices. So I am going to take it as K minus 2. K minus 2 edges it is there, because K1 plus K2 is nothing but the total number of vertices. So now, so here it is, what is this? T1 plus T2 is nothing but the total, the given tree minus one edge I removed. T1 plus T2 is nothing but how many edges it is having? The number of edges it is having in T minus E. So T minus E, which is nothing but T minus E is equals to K minus 2. K minus 2. So whenever, if it is having T minus E is K minus 2, then T is equals to this edge I am taking to that side, then automatically I am going to say that it is K minus 1 edges. K minus 1 edges. So here, then the less than this is, so what I am going to get? T1 minus edge is consisting. So the T is what? T is nothing but which is having K plus 1 vertices. Consequently, T is exactly having K minus 1 edges, and so that the theorem is true for, N is equals to K plus 1. N is equals to K plus 1. Subsequently, we can say that the theorem is true for all the values of N. All the values of N. So here, let us once again, the theorem we are going to prove this, and it is obvious for M is equals to 1, that is N is equals to 1, that means the number of vertices are 1, or number of vertices are 2, and the number of vertices are 3. And we are going to assume that, the theorem is true for number of vertices are K and lesser than K vertices. Now we are going to prove that the theorem is true for a tree which is having K plus 1 vertices. Then if we are going to prove that it is true for this, then obviously it is also true for all the trees which are having any number of vertices. Okay, so for that, let us consider we are taking a tree which is having K plus 1 vertices. Or else we can say that whenever here it is T1 and a tree true, or else we are going to consider, instead of taking K plus 1 vertices, we are going to, the induction step is lesser than K, it is true. So for that we are going to take a tree which is having K vertices, So whenever if it is having K vertices, then automatically, if I am going to remove any one edge, then it will become less than K number of vertices, So whenever if I am going to remove E edges, then it is going to be become two components. One component is T1, another component is T2. So T1 is having K1 vertices and T2 having K2 vertices. Obviously, K1 and K2 is less than K. Obviously, K1 and K2 are less than K. Subsequently, the theorem is holds for lesser than K value, K vertices. So we can say that T1, number of edges in T1 is nothing but K1 minus 1. T1 number of edges are K1 minus 1. And the number of edges in T2 is K2 minus 1. So number of edges in T1 plus T2 is K1 plus K2 minus 2. K1 plus K2 minus 2. So what about T1 plus T2? T1 plus T2, which is nothing but T minus E. T is the given tree which is having K number of vertices, and we removed one edge. So total number of edge, whatever the T is having, minus one edge, which is equals to, this is nothing but K. K1 plus K2 is nothing but K number of vertices minus 2. So t is equals to, there is a number of edges it is having. So k minus 2 and plus 1 edge. So subsequently k minus 1 we are going to get. And the tree is having only k vertices. So number of edges in this tree is nothing but k minus 1. K minus 1. Hence we can say that this is true for all the trees which is having any number of vertices. So here we just take that the theorem is true for a graph which is having n is less than or equal to k vertices. Then we can consider n is equals to k vertices, and we prove this result. Obviously, it is true for all the graphs, all the trees which are having any number of vertices. Then the another one is any connected graph G with n vertices, n minus 1 edges is a tree. Any connected graph that we have to consider, and which is having n minus 1 edges, then it is a tree. It is a tree. So here let us consider G is a connected graph with n vertices and n minus 1 edges. Now we are going to prove that G is a tree. So G is having n vertices and n minus 1 edges. So we are going to prove that it is a tree. It is a tree. So let us assume that it is not tree. It is not tree. So we are going to assume that this is assumption. This is assumption that we say that it is not true. If it is not true, then it is having a cycle. It is having a cycle. So if it is having a cycle, definitely there is between any pair of vertices, or at least one pair of vertices will have more than one path. Or else I can say that G is not a tree. So G contains a cycle. Let us say that the cycle is the cycle we are going to consider. We are going to consider. So I am going to take it as like this. So like this. So if it is a cycle, let us say that this is an edge, and then if I am going to, this is the graph G, and G is not a tree, so it is having a cycle. What about G minus E? G minus E is also connected. But G minus E is having n minus 2 edges. See here, this is also having n minus 2 edges. So here 1, 2, 3, 4, 5 edges, and then it is having 3, 4, 5, 6. So it is a 6. It is having G minus E. So whenever if I am going to remove this, so it is having n minus 2 edges. So it is not a connected graph. G minus E is not a connected graph. So which is not true. So here is I am just saying that if I am going to remove this, still it is connected. Still it is a connected graph. So here whenever if I am going to remove any one edge, so the graph will be disconnected. Then only we can say that there is a possibility of n minus 1 edges. But here, if I am removing one edge, still the graph is connected. G minus E is also connected. So which is not true. That means whatever the assumption we made that the graph is not a tree is wrong. So the graph is a tree. So that's right. So here what is given, once again I am repeating. So here G is a graph which is having n vertices and n minus 1 edges. We are assuming that it is not a tree. It is not a tree means it is having a cycle. But what is given? G is a connected graph and n vertices and n minus 1 edges. It is given. So whenever G will not become a disconnected, if I am going to see if it is having a cycle, then what I am going to do, if I am going to remove any one edge between the vertices U and V, let us say, So the graph will not become a disconnected. The graph is not a disconnected. So the graph is not disconnected if E is removed. If E is removed. So if E is removed, then the graph is not disconnected means G minus E, which is still connected, which is having n vertices and n minus 2 edges. N minus 2 edges. Therefore, it is having n vertices and n minus vertices I am not removed. But edge if I am removed, then it is n minus 2 edges. Then which is a contradiction to the hypothesis. If it is having n vertices, then definitely the edges are n minus 1. So it leads a contradiction. So our assumption made that the G is not a tree is wrong. So G is a tree. Next, a connected graph G is a tree if and only if adding any edge between any two vertices in G creates exactly one cycle. So first, we are going to assume that the given graph is a tree. Then we are going to prove this. And conversely, if I am going to take this and we are going to prove this. Suppose the graph is a tree, then definitely it does not have a cycle. By theorem 1, it has only one path between every pair of vertices. So any two pair of vertices, U and V. If you add any edge between U and V, then there is an additional path created by U and V, and two paths constitute a cycle. Since G has no cycle earlier, this is the only cycle which G now possesses. So, which is having, that means whatever, by adding any edge, then two vertices creates exactly one cycle. This is obvious. So what we are taking, the graph is a tree. Whenever the graph is a tree, it does not have any cycle. By using first theorem, then definitely it has one path between any two vertices. Let us there U and V. If I am going to create one more path between U and V, that leads additional path between U and V. So existed path and additional path will constitute a cycle. Since G had no cycle earlier, then now G will possessing a cycle. So this is the first result. And conversely, we are going to consider this and we are going to prove that the graph is a tree. So whenever it is obvious, suppose the graph is connected and adding any edge between the two vertices and it creates exactly one cycle. This implies that before adding this edge, exactly there is one path. So we can say that this implies G is a tree. Now, another definition, minimally connected graphs. A connected graph is said to be minimally connected if the removal of any edge from it and the graph is going to be disconnected. Then it is known as a minimally connected graphs. Now, another one, a connected graph is a tree if and only if it is minimally connected. So suppose first we are taking the a graph is a tree, then we are going to prove it is minimally connected. And conversely, if it is minimally connected, then we are going to prove that it is a tree. Now, so here the graph is a tree we are taking, then it does not, it is assume that it is not a tree. So here, suppose we are taking G is a connected graph, but it is not a tree. Then definitely G contains a cycle. Whenever if it is having a cycle, if I am going to remove any edge from this cycle, the graph will not be disconnected. If the graph is not disconnected, means it is not minimally connected. So whatever the connected graph that we are assuming that it is not a tree, leads it is not a minimally connected. Then the equivalently we are going to say that, if it is a connected graph which is having a tree, or if a connected graph is minimally connected, then it is a tree. This is nothing but a contrapositive. And now the conversely. So once again I am repeating. So suppose the graph is a connected graph we are taking and it is not a tree. If it is not a tree, then it forms a cycle. If it forms a cycle, if we are going to remove any one edge, the graph will not be disconnected. Implies the graph will not be a minimally connected. If it is not a minimally connected, why I am getting a connected graph? G is not a tree, leads G is not a minimally connected. And we are going to take it a contrapositive. If it is a minimally connected, the graph is minimally connected, implies it is connected and it is a tree. Then conversely, suppose G is a connected graph which is not minimally connected. Not minimally connected means if I am going to remove one edge, still it is connected. Still it is connected means E must be, it forms a cycle. Even though if I am going to remove one edge, so it is still connected. So if the graph is not a tree. So what I am, this is nothing but, if a connected graph is not minimally connected, then we are getting a connected graph which is not a tree. Once again, contrapositive, if I am going to take that, then if I am going to take the contrapositive, if G is a connected graph and is a tree, then it is a minimally connected. Let us go for some examples related to this. Prove that a graph with n vertices and n minus 1 edges and no cycles is connected. A graph G which is having n vertices, so n minus 1 edges, and does not have cycles, then we have to say that it is a connected. So no cycles. So let us say the graph is not connected. So whenever the graph is not connected means it is having a components. So each component is a subgraph. Let us the components I am going to take H1, H2, H3 and so on HK. Each component is a subgraph and let it be H1, H2 and so on HA. So each H1 is having some vertices, let us say N1 vertices, and this is H2 is N2 vertices, H3 is N3 vertices and so on, HK is NK vertices. Then, and each is a connected component, each will have not having any cycle and moreover it is a connected. So each one is a tree. So each one is a tree means how many edges it is having? N1 minus 1. This is N2 minus 1. This is N3 minus 1. And so on. And this is NK minus 1. These many edges are there. So what about the total number of edges are? N1 minus 1 and N2 minus 1 and so on NK minus 1. So which is nothing but N1 plus N2 plus and so on plus NK minus 1. How many times it is repeated? K times. So this is nothing but the total number of vertices. So this is N and next this is K. So it will become N minus K. So what about N minus K? It is having these many number of edges which is equal to the total number of edges. Which is not equal to the total number of edges. What is the total number of edges? It is N minus 1. The total number of edges are n minus 1. So I am taking that it is the graph is having n vertices, n minus 1 edges. This is the assumption made. N minus 1 edges. So total number of n minus edges, what we are getting, n minus k, that is equals to n minus 1. So which implies what I am going to get? K equal to 1. K equal to 1 means k is nothing but the number of components. Number of components should be 1. Should be 1 means if I am taking the graph is not connected, if I am taking the graph is not connected, but I am getting the components are 1. Components are 1. So that definitely it should be a connected graph. Definitely it should be a connected graph. So this is the way that we are going to do. So first we made that it is having n vertices and n minus 1 edges, and we assume that the graph is not connected. The graph is not connected. Connected means not connected means it is a disconnected. This is disconnected means it is having a components. It is having a connected subgraphs. Those connected subgraphs are nothing but a component. Those connected subgraphs are H1, H2 and so on. Each H1 will have N1 vertices, H2 will have N2 vertices and so on. Then the sum of all these vertices will become N, and next each and every subgraph does not have any cycle, so it is nothing but a tree. So each and every one will have n minus 1 edges, n2 minus 1 edges, n3 minus 1 edges and so on. Subsequently, if I am going to add all the things, we are going to get n minus k edges. But what is given in the problem itself? It is having n minus 1 edges. So n minus k must be equal to n minus 1. So we are going to get k equal to 1. K equal to 1 means it is nothing but the number of components equals to 1. So it is there is no component, there is no subgraphs will be there. The entire thing is connected only. The entire graph is only one connected graph only. So whatever the assumption we made, the graph is not connected is wrong. So if it is correct, then I am going to get k is greater than 1. K is greater than 1, but I am getting k is equal to 1. So whatever the assumption we made, that is wrong. Hence, J is a connected graph. Next, another one. F is a forest with k components. If n1 is the number of vertices and is the number of edges, then prove that m is the number of edges. Let us say here it is missing. M is the number of edges. Sorry, here I am missing. M is the number of edges in forest. Prove that n is equals to m plus k. So it is given it is a forest. It is a forest means it is a disconnected graph. Altogether we have to take each and every subgraph is known as a component. It is having, let us say for F is a forest means it is having some components. It is having some components. Let us say it is having k components. K components. H1, H2 and so on. This is H1, H2 and HK I am going to get. There are k components. And each component will have some vertices and some edges. So let us say H1 is having n1 vertices, H2 having n2 vertices, like that it will be. So, and next another one is, so we are going to say that H1 is n1 vertices, H2 is n2 vertices and so on and so on. And definitely it is having some number of edges. Let us say it is having m1 edges, it is having m2 edges and so on. Mk vertices and mk edges. Mk edges. So here, whatever these total number of edges are, m1 plus m2 plus and so on, mk which is equal to. So h1 is a one component. It is having n1 vertices. So it is a connected cycle-less subgraph. So it is nothing but a tree. So it is having n1 minus 1 edges. And the second one is also having n2 minus 1 edges and so on. So last one is having nk minus 1 edges. So here this is nothing but the total number of edges, let us assume, we are taking it as m. So this is equal to m. Then it is n1 plus n2 plus and so on plus nk minus how many times 1 is repeated? K times. So it is nothing but the total number of vertices minus k. Total number of vertices minus k. Then n is equals to m plus k. N is equals to m plus k. So this is the way that we are going to prove that this example. So in the next session, we are going to discuss some more problems related to this. With this, I conclude this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.